Hello, everyone. Good to see you here. I'm going to talk about the project funded by PDI last year on fast and reliable characterization and quality assurance of fabricated CLT panel using ultrasound method integrated with an AI-based framework. I'm going to present on behalf of a team with my co-PIs, Lech Mezinski and Mario Paula Riggio, and a couple of grad and undergraduate students helping us with this project. And there is a huge synergy with the types of project that Lech is running. So he did a fantastic, basically, talk on the challenges related to CLT panel inspection based on the PRG 320. So thank you, Lech. So you made basically my job very easy. The random sampling for CLT quality assurance may lead into basically poor judgment about the overall reality about the bonding integrity delamination situation. And what was the motivation for this project was that, is there a way in the manufacturing system that we come up with a more reliable and at the same time cost-effective, and fast method? And we decided to choose to review different types of non-destructive testing for quick inspection of CLT panel during the manufacturing process. The chosen method was ultrasound for several reasons. It's relatively very affordable compared to some other types of non-destructive evaluation. It could be portable, so it could be practiced both contact and non-contact based. And also the team had the history of working with different types of wave propagation techniques, based on which the proposal submitted to TDI was narrated. We are using a set of ultrasound machine with both longitudinal wave and shear wave for CLT panel inspection. We're collecting the ultrasound signal. So we send the wave and then we receive the wave through transmission process, and then by analyzing the characteristic of the received signal, we're going to talk about the quality of the CLT cross-section, through that propagation path. Mainly, the assumption is if there is any discontinuity in the material, if there is any poor bonding quality, it could be captured by the wave we receive, we collect, and it could be used as a basic for developing a predictive framework. So before doing the experiment, we spent a couple of months identifying the challenges of applying ultrasound using manual measurement, because especially for industries who are here, if you want to go and get automated ultrasound setup, that's also an option, but so it's more costly. Even for academic purpose, the difference between a manual setup and an automated is between, I don't know, 10 to 20K, all the way up to 100 to 200K if the panel is going to be, inspected automated. In this case, we are using cheap, affordable sensors, but then the problem is we have to, measure every point manually. And there are some factors affecting the accuracy and consistency in the measurement. One of them is when you're applying the sensor, by hand, how much pressure you put on the sensor. And the coupling between the sensor and the substrate, it's going to hugely impact the collected signal. So here, we did a bunch of different experiments. We tried different types of ultrasonic gel or no gel, or even putting some rubber in between the transducer and the CLT surface, and we look into the variation in the signal acquired. We try to see how much variation we have when we send the wave longitudinally or in transverse direction in the CLT specimens. Also, what's the variation in the collected signal when the wave is acquired, manually versus some sort of setup that the grad students came up with. It's a very, very cheap but It's a very smart setup. So it's basically based on a spring design. And then there is a PVC basically case in which you're gonna press that. But then because of the spring, inside the case, you are going to apply consistent pressure every time just to make sure that manual measurement is not gonna cause a huge variation in the collected data. With that, we will start working, and here there is a huge synergy with the project. LEC is basically leading on studying the impact of thickness tolerance and thickness variation in the bond integrity of CLT. So scan all the wood samples for a small CLT fabrication and compare the modulus of elasticity from the ultrasound data and compare it with that of measured by LEC's team using the DIC method. Also, on the small sample size with different gap, with different thickness variation in the CLT, we measured, so we send and receive the ultrasound wave and look into the differences. So here is one example. As you see, we did one measurement at the left side, at the right side, and at the center. And at the center, we have pieces of wood with thickness variation. And these are the corresponding wave measurement. Basically, it shows the time of flight, the time it takes for the wave to travel from one side to the other side of the sample. And we can see that it takes more time for the wave basically traveling at the center part of the CLT. That means that our measurement is very sensitive to thickness variation, and this thickness variation is under 1 millimeter, and it's going to be the basis for developing our data-driven framework. At the moment, students are working on running the delamination test on a small CLT blocks and trying to make correlation to the ultrasound signal features. So the next step in the coming year is to proceed to fabricating 4x8 CLT panels at Emerson Lab. And as LEC is going to study how the thickness variation is going to impact the bond integrity of CLT, we are going to scan the entire panel by ultrasound, trying to come up with some sort of heat map, identifying the spot with more manufacturing defects. It's going to be, at the end, a very, I think, practical and cost-effective practice for mass timber manufacturers to quickly look into the bond integrity and overall manufacturing defects and basically free them from costly and just randomly tested this, based on destructive methods, based on PRG 320. And in order to make the decision more unbiased by the human judgment based on the data collected, we are going to train some sort of machine learning-based, AI-based modeling in order to help us with more accurate pass and fail for decision-making. Another direction of the future study on this is to, at the end, trying to make the simple, basically to have dual function. What if the same system is going to be used for inspection of CLT panels in service, basically for building structural health monitoring? In that case, we may not have easily access to the other side of the CLT panel. So these types of technique, which is called true transmission, sending the wave from one side of the CLT and receiving from the other side, may not be an easy option. So I'm also very interested to look into this form of data acquisition called pitch and catch. So basically all the data is going to be collected from one side of the panel. Is it possible that we practice that for both identifying the manufacturing defects and for the damages, made during the panels, in service condition? And in that case, basically the wave we send and receive has more complex nature because as it travels, it's going to be decomposed into compression and shear wave component. And we need to do some sort of basically wave theory calculation. It's called Lamb wave theory, which in a smaller size solid wood, we had in the past successful implementation of this method. And we could predict both the modulus of elasticity and rupture of solid wood at different moisture content with a very, very low error. It was around 2% for the modulus of elasticity, much lower than the typical time of flight measurement. But what are the challenges when it's applied to large size CLT? It still need to be studied in the future. So at the end, we are hoping to come up with, a cost-effective method for companies for their panel inspection and try to develop a model that hopefully could be used both by manufacturers and construction team for assessing the remaining useful life of their CLT panels. Thank you.